conclude the first part, the largest one of the workshop, and on behalf of all the organizers, to thank all the participants, all the speakers, all the discussion leaders for doing excellent job. So it was very nice and fruitful. I mean, the discussions were very different. Each discussion were different, the different style, but they were all very nice. Thanks for that. And I want to give a final word to our chief of our theoretical department in Institute for High Energy Physics, that you can see on the background. This is our division actually. So please, Vladimir Petrov, please.
Okay. Is it okay?
Yeah, yes, that's fine. You can see it. So full screen mode, probably. Yeah. Start slides сначала. Yeah.
Okay.
Yeah, perfect.
Thank you very much for giving me the word, not in capacity of the chief or leader of theoretical division. I don't think it's very important. And first of all, I'd like to say that the workshop we have organized during this week seems to me very successful, because we urged participants to be not just attendees and to listen to presentations, but also to take part and actively take part in discussions. And that's exactly what happened. And all the discussion, as you could judge, for example, were very vivid, very interesting, and contributed a lot to the fact that our meeting is really the genuine workshop, because the hard work during all these 5 days. So today I have also what to do. I'm not going to go over all these items. They are very large, and also because any items were finished with discussion sessions, and during discussion sessions, all important questions were asked and answered. I don't want to spoil this good impression of these discussions. And let me also only to add some remarks, maybe, which are not very stupid, and maybe will be useful for you. So let's go to this direction. First of all, hot problems of strong interactions, the title of our meeting, actually mean that hot is not just the urgent problems, but also the problems related to non-zero temperature. And non-zero temperature means thermodynamics, and thermodynamics, as we know from school books, but remember, it means, first of all, the large number of particles and small and negligibly small fluctuations. And macroscopic thermodynamics, I mean equilibrium thermodynamics, takes place when we have a very large number of particles, the Avogadro numbers with negligible fluctuations. And the reason for this negligibility of fluctuations is the time of life of the system is much larger than the relaxation time of several times. And also the volume and surface effects are suppressed like that. And this gives us the possibility to consider at least approximately the situation as equilibrium thermodynamics. Now let's see what we have in our case. We consider QCD, strong interaction. Strong interaction for us is the synonymous of QCD, quantum thermodynamics. In our case, concerning our discussions during this meeting, this means that not only chromothermodynamics, what we have in this case, what are experimental, so to say, requisites. I say about that, I mean, first of all, heavy ion collision. What is the number of particles? When number of particles, I mean the average number of particles, average multiplicity, which produced not from the remnants of heavy nuclei, but first of all from the central region, where the really we expect the formation of some compound, which according to our hopes may demonstrate thermodynamical properties. But when we see the numbers, we see that in contrast what we have within thermodynamics, I mean macroscopic thermodynamics. In our case, unfortunately, the conditions for formation of conditions for equilibrium thermodynamics are not very promising, I would say, because the relaxation time I have taken as a relaxation time the measure of it, even exaggerating, taking the PT average at 1 GeV, actually it's less. Then the ratio between the lifetime of the system and the relaxation time is too small to hope for the real thermodynamic equilibrium behavior and onset of the local thermodynamical relaxation and behavior. And also volume surface effects are not very small, so they influence very much. And in partly it was addressed in several excellent talks which created boundary condition and the influence on the effects which were discussed during talks. Now, one another item I would like to touch is the QCD as itself. I don't take into account some modification of QCD related to adding some hypothetical terms like theta term and other, but just a standard QCD is a T invariant. So if I imagine, for example, that I can calculate everything when I take two nuclei and imagine that I know exactly how to calculate the amplitude of strong interaction, then I can calculate everything, amplitude, total cross-sections, differential cross-sections, any kind of experimental signatures. And when I obtain this result, I do not see a place for temperature or something like that. And where the temperature means irreversibility, the creation of entropy, and where the source of this entropy production, it's a question to me. I tried to ask some people, some participants in my private discussion during this conference. I did not obtain, unfortunately, a satisfactory answer to that. Maybe they are. If you have some, please write me to my mail. Now, some people think even the possible source of this irreversible behavior, this chaotic behavior, which is known that even in classical mechanics, if you take, for example, a three-body problem, you can obtain there the chaotic behavior, and this could be considered as some kind of or some source of irreversibility. But I don't think it's highly promising. It's highly questionable, I believe. Okay. Now, closer to our subject, how to introduce entropy and temperature into the realm of the quantum field theory. What is normally suggested is, even though you don't know what is the chunk of matter you have in your hand, if you take the just formalism of quantum, even quantum mechanics, not even quantum field theory, quantum mechanics also, the people invite entangled states which give them density matrix description, and density matrix may be related to the Shannon informational entropy or Poincaré, maybe some people call it Poincaré entropy. And this information entropy is related to more or less, I don't know, shaky or not, or some way with statistical entropy. Then you can try to derive the gift distribution. The gift distribution asks for existence of the thermostat. So, and this exponential expansion gives you what people use as input for formulate the thermal field dynamics. But this is only formal thing which is easily made, and the rest is a matter of calculation. But the principal thing, how we can obtain these conditions for that, and not to take into account, for example, the further terms of this expansion around the, and what is thermostat in general, because, for example, in heavy ion collision, no traces of thermostat you can even imagine. So our system is in vacuum, it expands, and we only can hope that some kind of time it will pass in a situation of at least approximate thermodynamical behavior before coming to hydrodynamic expansion and so on. Now, coming to Quark-Gluon Plasma, several very brilliant talks were made in this way. I don't want again to spoil the very interesting results which were shown. Just want to remind you that one of the very powerful sources of money was that the financial agencies were very much impressed, to my knowledge, that LHC should receive money because it may create first instance of the universe. And this belief is not only the mass theory, but some people, I mean, among physicists also believe that this is the fact. But I want just to say you that the first instance of universe is very difficult to create, because in the tunnel of LHC, for example, you create something in surrounding vacuum, in surrounding space-time. But when you consider the first instance of the universe, you have no space, no time also. They are created simultaneously. And if you take, for example, the geometrical terms, then we have to create not only the such interesting mixture we call Quark-Gluon Plasma, but also very huge curvature that we know in our situation, because gravitational fields certainly in the LHC tunnel are negligible. Now, during this conference, I learned very interesting very interesting thing. And novelty, I learned that there exists a morphological thermodynamics. It's very nice. I like very much the name. And my expectation now is that maybe next meeting we'll see syntaxical thermodynamics. Just kidding. Sorry, let's go further. And our next session, I'm sorry that we made conclusive talks before the heavy quarks, which is just a lot of time. But nonetheless, I can envisage what will be said in this maybe also very interesting session. And the problem is that, first of all, this subject, I mean, heavy quarks, is tightly related to what we have discussed during these 5 days in the framework of some dynamical approaches, because heavy quarkonia, they can use and can serve as a thermometers of Quark-Gluon Plasma, and that's very important. But also there is per se itself heavy quark subject is very interesting, because after recent times we had no hadrons which were composed of more than 3 quarks, of quark and d-quark. And during several years which passed before, we have seen that new states were discovered, and I want to say that some of these states were predicted in our institute and the group of Professor Likadet, multi-quark states, I mean the pentaquarks and tetraquarks. But now the riddle is why no light tetra, penta, etc. quarkonium are observed, and I think this is a very good subject for discussion and so on. And so in conclusion, I'd like to say again, many people already said during this conference, that what we have observed at this conference, this meeting, at this workshop, which is really a fantastic progress in quantum thermodynamics. And I want to say that in some sense it was maybe a record of our series of conferences, because never before we had so many participants, up to 300 of them, and the number of people who actually took part every day was no less than 50, even by the late evening, and that's very joyful fact. So in spite of this fantastic progress in quantum thermodynamics related to thermodynamical issues, there remains something to think about, and part of this something I tried to show you. And let me now thanks all and everybody of you with your participation. And the only thing I can regret that we cannot organize to keep the joint drink. It's a pity, because always visit our conferences. But I hope that maybe in future we'll have such an opportunity, and we'll join around the table and to raise our glasses for physics and for our success in that. And now, to conclude, I want to say you that you have to take care among all these damned melodies. So again, thank you very much. Hope to see you in future in good health and with great scientific success. Thank you.